Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. Here we are with chapter 2 of microwave engineering. In this chapter, a family of microwave tubes that have a linear beam with respect to the magnetic field that we have considered. The very popular two-cavity klystron working as amplifier with the extended values of the gain and the performance. We have seen the multi-cavity klystron also. For oscillation purpose, generating the microwave reflex klystron is covered, and now we are going to see traveling wave tube. So before going to see the traveling wave tube, it is very important what exactly the slow wave structures are there which are having a vital role in the operation of traveling wave tubes. So let us see the details. So here we start with our topic, slow wave structures. So as before, in this chapter we have gone through the understanding of two cavity klystron. So before two cavity klystron, which was popular as amplifier, we have seen the limitations of the conventional vacuum tubes when they were operated onto the high frequency. So one of the limitation there it was, that is the gain and bandwidth product limitation. So for any electronic circuitry, the product of the gain with respect to the bandwidth is a constant here, and for the circuitry, if you try to achieve the higher gain, we have to pay in terms of the bandwidth, or for the applications where we want higher bandwidth to be the operating here, so the gain is reduced. So in case of the resonant cavities simply, or the resonant circuitry, for application onto the high frequency, the inductance and the capacitance values have to be maintained at minimum so that the operating frequency will be there. So for that particular limitation, there were a lot of ideas to overcome that particular gain bandwidth limitation, and in those ideas, slow wave structure use is the one. So for the case of two cavity klystron, reflex klystron, multi-cavity klystron, we have been used the re-entrant cavities. So it is a modification of a simple cylindrical cavity, we can say here. So here we have another one, that is slow wave structure. So as we have seen that for the microwave tubes, the principle of operation is based on velocity modulation. So here in the microwave tube, we have the two electrodes that are cathode and the collector, which is supposed to be the anode, positively charged. So electron beam is focused from cathode terminal to that of the collector terminal, and then there is to be the interaction of this electron beam with that of the microwave signal, if it is to be amplified in the case of two cavity klystron or multi-cavity klystron, or we have to generate the oscillations here. So in traveling wave tube, that will be our subsequent topic, we want the interaction of the microwave signal with the electron beam. So slow wave structure is the structure which is meant for making more and more interaction between the microwave signal and that of the electron beam focused in between the two electrodes of the microwave tube. Now there are several types of the slow wave structures. We have the few, along with the help of diagram we shall be explaining. So here we have the 5 types of slow wave structures, A, B, C, D and E. The first one, that is small a, we have represented for this kind of slow wave structure, is very popular. The name to this slow wave structure that I give nomenclature here, this is the helical line. The second one we have represented with the help of B. The structure you can see, and with respect to the structure here, for making more interaction of electron beam with the microwave signal, we have this folded back line. The third one, here we see a zigzag fashion, hence the name of this particular transmission line is zigzag line slow wave structure. Next to that, here we have D slow wave structure. The name is interdigital line. And the last one, here it is seen in terms of small e figure. So this line is corrugated waveguide. So out of these 5 slow wave structures that are meant for adjusting the velocity of a signal, we can say in simple, so that there will be more and more interaction of electron beam and the microwave signal. The very popular case of helical line we take. So for detailedness, we take this diagram separate out. Now here you see a helical transmission line. So generally here it is the cross section that we see for a cylindrical. So generally for the helical line, it is inside a cylindrical structure. So cylindrical structure may be filled with some kind of dielectric also. So this is the cross section with these two horizontal lines. You can imagine a cylinder here, and inside this cylinder we can have the helical line. So helical line is actually our slow wave structure. So to have some mathematical formulation with respect to the dimension of this helical line, here we mark for one turn of this helix. The difference between these 2 points we give for the distance denoted by small p. So small p can be called as pitch of this helix, whereas the total number of turns that we go with this particular case, we can have one constant small or capital N that will shall be denoting it further. So here it is the pitch. Now this is one dimension along this particular side, and along this side we can have the diameter of this helix. So for denoting the diameter of this helix, we can use the letter small d here. So here we have pitch denoted by small p and the diameter d. So the radius, it will be d by 2 here, and if we go for one turn of the helix, so it will be having the periphery or the circumference denoted by 2 pi r. So denoting it in terms of d only, we shall denote it by pi d. So here with respect to the circumference, it is a measure of length, and with respect to the pitch, so it is also a measure of length between the two adjacent turns of the helix. Here we can have a triangle here. So let us say this is small p, and this one that is represented by pi d here. So now it will be having a 90-degree angle in between, and here we can show the hypotenuse. So according to the Pythagoras theorem, we can show the length of the hypotenuse, that is under root of p square added with pi d square. Now for the help here, we take the angle between the hypotenuse and the pi d side, that we represent by symbol psi here. So psi can be treated as or named as the pitch angle here. So now when this helical line working as slow wave structure can be used into the popular traveling wave tube, our next topic, you can imagine that through this helical line there it will be the propagation of one signal here, and through the center of this helix there it will be the focusing of electron beam from cathode end to that of the collector end. So we want the interaction of the signal propagating through this helix and the electron beam that is having the axial direction to have more and more interaction with each other. So now here we can have one ratio, the mathematical ratio with respect to the phase velocities of the signal propagating through the helix and the another one. So here we can represent it mathematically as v suffix p divided by c, given as here we have the use of the pitch denoted by p in the numerator, divided by in the denominator here we have square root of p square added with pi d square. So as we see the geometry in this triangle, this is the angle psi here, so this ratio can be denoted as sin psi here. So let us say this is equation number 1. So with respect to this particular equation, we can mention here we have used in the denominator of the left hand side c. So c value is equal to 3 into 10 raised to the power 8 meters per second. So this is actually the velocity of light in free space. Whereas P we have denoted as pitch of helix. The next parameter, that is small d, it is diameter of helix, and the psi here we have, that is pitch angle. Now as usually the helix will be inside a certain cylindrical structure filled with certain dielectric. So considering the dielectric here, we can have the re-representation of equation number 1, and we can write it as V suffix P epsilon here, epsilon with respect to the dielectric constant or permittivity of the medium. It shall be given by P divided by, here we have square root of, here we first of all mention mu epsilon here, in the square bracket we have P square added with pi d square. So as for the case of free space, we know that the velocity is a denotion of 1 upon square root mu 0 epsilon 0. So that particular value is nothing but the 3 into 10 raised to power 8 meter per second. So if it is not the free space, some another medium, so mu 0 will be simply the mu here, epsilon 0 will be simply the epsilon here. So in the earlier formula, 1 upon under root mu epsilon denotes the velocity of the signal in that particular medium. So let us say this is equation number 2. So now for the helical type of slow wave structure, we consider a very small value of the pitch. Along with, we consider the free space to be the medium surrounding to the helix. So with respect to the phase velocity of the signal propagating through the coil, we can have the simplification into the formula. So we can approximate V suffix P to the ratio that is having PC divided by pi d. So according to the definition of the phase velocity, we must relate it to the ratio of omega and that of the beta here. So beta is the representation of the phase shift constant as far as the propagation of the signal is concerned, and omega is the angular frequency with respect to that signal. So let this will be the equation number 3 here. So as we have here the two parameters with respect to the propagation of the signal, that are omega and beta, here we have one special diagram with respect to computation of the phase velocity here. So in this diagram, the horizontal axis will be representing the value of the beta here, whereas the vertical axis will be representing omega here. This diagram is called as, here I name, Brillouin diagram, or simply we can write omega versus beta diagram. This diagram is very helpful. In this diagram, we see this dashed line that represents the ratio of omega with respect to beta for the free space here, so that we can simply represent by small c here. And for this solid line, we have the earlier formulation into the equation number 3 that has represented V suffix P is equal to PC divided by pi d, that is nothing but omega upon beta. Now here we have the 0 marking, we can say. This diagram is very helpful, as if we have the known value of beta on this horizontal axis, there it will be very much useful for the computation of V suffix P here, the phase velocity here. Now as we know the phase velocity here, the group velocity can also be determined from this particular diagram. So a mere slope is to be taken here. So here we have a new equation to represent. So for representation of the group velocity, we can denote V suffix gr computed by, here we have del omega by del beta. So from Brillouin diagram, here we have the partial differentiation of omega with respect to that of the beta here, or the differentials of this omega and beta when are having this particular ratio that represents the group velocity. So let us say this is equation number 4 here. Now, in order for a circuit to be a perfect slow wave structure, there it is one essential need, that the circuit should follow a periodicity property. The periodicity property for a circuit can be given with the help of one theorem. That theorem here we have. The theorem is called as the Fouquet's periodicity theorem, and the statement for the theorem can be given as the steady state solutions for the electromagnetic fields of a single propagating mode in a periodic structure have the property that fields in adjacent cells are related by complex constants. Now, to look at the statement of this particular theorem, we can have the mathematical representation. So here we can represent capital E as a function of x, y, z minus capital L, given by the representation of capital E as a function of x, y, z in multiplication of the complex here. So the complex constant here we have e to the power j times capital beta suffix 0 into capital L here. So here capital E as a function of x, y, z is a periodic function, and it is periodic function with the period represented by capital L here. Now beta we generally represent for the phase constant here. So in this equation, let us say the next equation number, it is equation number 5. Beta suffix 0 is the phase constant in the axial direction. And also the phase constant is with respect to the constant velocity of the electron along this axial direction here. Now it is postulated that the solution of the Maxwell's equation into the periodic structure can be written in the form that we have E as a function of x, y, z given by f of x, y, z into e to the power minus j beta suffix 0 into z. So in this particular equation, let us say this is equation number 6. F as a function of x, y, z, here it is a periodic function. The periodic function for the propagation towards the z direction with the period that we have represented earlier by capital L here. Now the capital L is the period of the slow wave structure. Now with the help of Fourier series and using the fundamental period represented for slow wave structure by capital L, we can have the representation of the field distribution function capital E. So by the next equation, we denote capital E as a function of x, y, z in terms of Fourier series by the summation operation having the index term n ranging from minus infinity to infinity for capital E suffix n in bracket x, y into e to the power minus j in bracket here we have 2 pi n divided by capital L into z into here we have another exponent e to the power minus j beta 0 into z here. So by the next step we can rewrite this as simply summation n is equal to minus infinity to plus infinity for en as a function of x, y here into e to the power minus j. Here we can denote beta suffix n here into z. So let us say this is the next equation, equation number 7 here, and this will be the left hand side, E as a function of x, y, z. So in this equation onto the right hand side, there it is n as a suffix for 2 times to represent en as a function of x, y and to represent beta suffix n here. So in this equation we can write the details like where en of x, y can be given by the formulation for the period of capital L. So here we have 1 upon L integral 0 to capital L here, operated over E as a function of x comma y comma z here into e to the power j in bracket. Here we have 2 pi n divided by L into z into dz here. So here for this particular equation we can name it equation number 8, and this left hand side denotes the amplitudes of the n harmonics of the signal here, and correspondingly beta suffix n can be given as beta suffix 0 added with 2 pi n divided by L. So this is the phase constant for the nth modes, and this n can be given right from minus infinity up to, let us say, minus 1, 0, 1 up to plus infinity. So the complete range here we provide for the number of harmonics here. So to look at the above equation with the help of the Fourier series representation, we can say that signal into the periodic structure can be represented with the same frequency but expanded over different phase velocities here. So therefore we can have the representation of phase velocities for the nth modes. So here we have v suffix pn here, and it will be given by omega divided by beta suffix n, and here we can therefore denote omega divided by the earlier formula of beta suffix n. So here we write beta suffix 0 added with 2 pi n divided by capital L, the period of the helix here or the periodic structure here. And also, as here we have the phase velocity for nth modes that I outline here, we can also represent the group velocity. The group velocity can be represented v suffix gr, and here it can be given as, here we have d as a function of beta 0 plus 2 pi n divided by L here divided by d omega. So it should be in this inverse of the square bracket can be simply represented as, here we have del omega with respect to del beta suffix 0 here. So here for the group velocity we can say that v suffix gr is independent of n here. So I mention here. So as we have the representation of equation for n number of spatial harmonics, the diagram relating omega with respect to the beta can again be given. So here this diagram can be again said to be the Brillouin diagram. So on the horizontal axis we have beta relating to the values of omega onto the vertical axis. So here I name here Brillouin diagram for the n number of spatial harmonics. So here in this particular diagram, as you can see, this particular side represents the ratio omega with respect to that of beta here, and for the free space region it is nothing but the velocity of the light c here. So in this diagram the information can be obtained that there will be the propagation of the electron beam along the positive z direction when the n is having the negative values with respect to the spatial harmonics. Another thing in this diagram, here we have the shaded region. The shaded region can be named as forbidden region. The forbidden region is for the case whenever the phase velocity will be exceeding the velocity of the light. So in that time the structure that we have as a slow wave structure will be starting as radiation. Therefore this particular region is taken as forbidden region. So this was the overall analysis of the slow wave structure, the very popular helical type line we have analyzed here. So with this understanding, in the next lecture we shall be starting the helical type traveling wave tube here. So it can be abbreviated as TWT. So I hope you are definitely getting benefited by the knowledge we share for microwave engineering. For more such information, you can subscribe to Ekeeda channel. Thank you.